Good morning, everyone, and welcome to the webinar by Molecular Vista, Photo-Induced Force Microscopy, or PIFM, Nanoscale Hyperspectral Infrared Chemical Imaging. This webinar will be hosted by Ryan Murdick and myself, Tom Albrecht. The first speaker who's going to introduce the concepts and the way this technique works will be Ryan Murdick. I'd just like to remind you all that we'll be taking questions, and you're welcome to type them in at any time, and we'll address them at the end of the webinar. So with that, Ryan, please go ahead and start the presentation.
Okay, thanks, Tom. Yeah, as Tom mentioned, the way we're going to format this is I'm going to introduce the concepts and how it works, and then in the second part, Tom's going to get into the applications. We gave our first webinar in May of this year, and this summer we've had even more exciting results that have expanded the scope of capabilities for PIFM, and Tom's going to present those. But I'll lay the groundwork, and then I also just wanted to mention that in a couple of weeks we're going to be at SciEx in Minneapolis, September 18th through 23rd. So if you'd like to drop by our booth, we'd love to see you. A little bit of background on Molecular Vista. It was founded a few years ago by Sung Park, who was co-founder of Park Scientific Instruments, and so he's been in the AFM world for 20 plus years, an industry veteran. And then also Kumar Wickramasinghe is one of our co-founders as well. And Kumar is nothing short of the godfather of most AFM modalities. He's invented techniques such as scattering snow, apertureless ensom, dynamic AFM, EFM, MFM, Kelvin probe, force microscopy, and not even listed there is PIFM, which is what this talk is about. And so and PIFM is a very young technique. Kumar published the first paper there with his group in 2010, and he's now at the University of California, Irvine. But that gives you a little bit of history, a little background on our company. In brief, so what does PIFM do? It's going to provide you the opportunity to have 10 nanometer scale chemical information, and you can actually achieve it routinely and on a wide variety of sample archetypes. And so that includes things like polymers. If you look on the right, this would be an example of a resonant material. It's the 1490 wave number there is because we tune the laser to the resonance of the polystyrene, so it's to the absorption peak. And so all the green there is actually where the polystyrene is. And Tom's going to go more into detail on the specifics, but I'm just trying to give you an overview of what types of systems, and it's very much not limited to this. 2D materials like molybdenum disulfide, molybdenum diselenide, graphene. These are non-resonant materials, and we still see very nice contrast. And even plasmonics, the number of samples we can study is large right now. It's vast, and it is growing. Now, how it works is that we actually are mechanically detecting the near-field signal. And so the same feedback electronics that are monitoring the cantilever position, we demodulate that in a clever way, along with modulate the laser in a clever way, such that we can actually extract out the near field from the mechanical response. And the spectral component is added by coupling a quantum cascade laser. And currently, it benchmarks at 800 to 1800 wave numbers. But I would stress that it's simply just adding a QCL to an AFM. It's not so brute force. I mean, there is a lot of refinements we've done in-house at Molecular Vista. There's things like pointing stability as you tune through the wavelengths. Does it stay focused in the same spot? And we've done a lot of refinements there with our QCL to where we really like how it operates now. We can span the whole spectrum of the QCL and just really pull a full spectrum. It's nice. How it's different is that we don't depend on a far field detection at all, and we don't depend on any plasmonic tip enhancements or any other tricks to discern near field from far field, because there is no far field detector. We're reading it out of the PSD that's monitoring the cantilever. The spatial resolution does not vary with the sample thermal properties. So there's another technique called PTIR, which I'm also going to dissect a little bit, where it also is using the mechanical sensor to read out the near field, but its spatial resolution is very limited by the thermal properties of the sample itself. And the last part, and we're really proud of this, is that it's very user friendly, and we've done a lot to make it so. Historically, near field techniques are not easy, and we wanted it to be different with this one, and so we've done a lot to actually make it as easy as just using an AFM. The motivation behind an instrument like this is that the idea is you want chemical information. Optical spectroscopy techniques are good at getting chemical information, but they're diffraction limited. And so to get below that diffraction limit, it's the wish list, if you will, is that at each pixel, can we get the chemical information as an AFM scans? And even better yet, at each pixel, can we get a full spectrum? And the answer to that is yes. And I'll be dissecting that more. But basically, the engine of it then is a scanning probe microscope, because those are very good at getting below the diffraction limit very routinely. In fact, atomic resolution with STM or AFM is very, very easy to do these days. And so how do we marry the two? So the chemical specificity that one gets with optical spectroscopy with the spatial resolution of something like scanning probe microscopy. And so I just want to touch on this again with the difference between a technique where you're reading far field light and playing some trick to distill the near field from the far field. Here's an example of that. This could be a scattering SNOME experiment or a TERS experiment where there's a far field light source. It illuminates the tip sample junction. You collect everything, all of it. And then if they're, in the case of TERS, if you have a really strong plasmonic field enhancement under the tip, that enhances the Raman scattered signals so that they actually become detectable. In contrast, a technique where you're actually using the cantilever's mechanical sensing properties to read out the near field. Here's PTIR. This is not our technique, but here they operate in contact mode, shine light on the tip. There's a ringing in the tip in the cantilever, which is read out by the PSD. So they also are using the feedback electronics to read out the response. And so as the cantilever rings at various points on the sample, if you draw an envelope over the magnitude of that ringing, you essentially have an absorption spectrum. But it's basically you're only sensing, it's got about 100 nanometer resolution due to the fact that it's influenced by where the heat has spread into the sample, which is usually in a radius of about 100 nanometers. So the response, the local response, is only for a local 100 nanometers typically. And so just to give a quick overview, it's TERS, NSOM, scattering type SNOME. They're going to use far field detection, and there's two techniques that use the cantilever mechanical properties: PIFM, which is our technique, and PTIR. And so how TERS works, here's a very typical TERS setup with inverted illumination. Light is shined both illuminated and collected from the objective lens below. Like I had mentioned, you really depend on this plasmonic field enhancement outside to actually enhance the signals. The tip needs to be close to the surface for signals, so modalities like STM and a shear force AFM tend to work better. Polarization, it's desirable to have it maximized in the tip axis. Side illumination, that it works with that too. There's this well-known issue with TERS is the tips, where if you etch 20 of them, maybe one or two of them will show TERS signal. And it's very common to see a gold substrate ground plane for the gap field enhancement. So there's a lot to make it actually work. And even with that, it usually only works on some selected samples that either have a strong Raman cross-section or other things. So scattering SNOME is another technique that's using far field collection. Their AFM is operating in tapping mode. The near field is scattered into the far field by the cantilever's tapping, but also far field gets scattered into the detector at that cantilever tapping frequency. So simply locking into the cantilever drive frequency to the dither and pulling out Nearfield doesn't work that way. You have to exploit the nonlinearity of the interaction. So the higher harmonics get populated with more Nearfield signal than the lower ones. But then also there's this issue with background subtraction. So it really needs to be set up with an interferometer for self-homodyne or pseudo-heterodyne to eliminate this parasitic far-field signal. And that can't be stressed enough, that without this running it like an interferometer, most of the data that you would pull out of there is far too ambiguous to actually interpret. It can be difficult to deconvolute signals if you have adjacent nanostructures and they're, say, nanometers apart. Where did that signal come from? There is a spectroscopic component that can be added to it via FTIR. And there is some information that scattering SNOME gets that PIFM doesn't, such as the optical phase through interferometry. You can get the real and imaginary parts directly. And so here's an example, a very nice result that had come out where this would be the spectroscopic component of scattering SNOME, where what they're doing is they're using a broadband light source, either through difference frequency generation or a quantum cascade laser, and shining the light onto the tip, and they set up a reference arm. And so the light that's scattered by the tip, they're actually interfering that with the reference, just like an FTIR. But with only 100 microwatts, which was used in this work, it's even less that's scattered off the tip. When you interfere those in the detector, that's not a super strong signal coming off there. So that spectrum there is an average of 154 interferograms, which took probably about 60 minutes. So it can be set up for spectroscopy, but it tends to be very slow. And just to touch on the other mechanical sensing near-field technique, PTIR, the way that works is that there's a pulsed IR source shined on the tip, makes the cantilever ring, and so it's these ringings, if you envelope them, that correlates very well with the absorption spectrum, with the bulk known FTIR spectra. So there is charm there. So it is a better than diffraction limited sensor of local chemical information, but it's ultimately sample dependent, because as the light hits the sample, basically the sample expands thermally quickly, and that's what exerts the force on the cantilever. And so depending on how far that the heat has transferred into the sample, that determines the strength of how hard it hits the cantilever, if that makes sense. And so the lateral resolution depends on the sample thermal diffusivity. And then also just the overall signal to noise of it is a thickness dependent entity, because if it has more depth to travel into the heat, then you can get better signal that way. But so a really thin sample, it's really difficult to make that work. And so, like I had said, typical resolution is 100 nanometers. There has the best reported is 20 nanometers using a gold substrate ground plane. And so now that I've given sort of an overview of what else is out there, how it works, I want to explain how PIFM works. And so if you think of a cantilever, which is a resonator, that's what an AFM is, by the way, is a resonator under feedback. And it's operating in tapping mode. So you have some, you're reading out topography at F0, which is this first eigenmode, the one that just goes up and down. If there's the next eigenmode up has a node in its oscillation. And so we found that, or Kumar found in 2010, so if you modulate the light source at some frequency such that when added to F0, it equals F1, we essentially are populating that eigenmode. We're using that previously unused sensor, and we project the image force onto that sensor. And so as we read out the topography, it's just another lock-in channel then is giving us the near-field amplitude and phase. And so here's a more general overview of it. And so you can see that the PSD, it's being demodulated one way for topography, one way for PIFM. And then our pulsed QCL, which is tunable from 800 to 1800 wave number, is shined on the surface. So as the tip is scanned over the sample, and what's shown there is block copolymers, it's depending on how the laser's tuned, we can tune it to actually be on resonant with either the polystyrene or the PMMA in this example, and generate an image of just that, of just PS or just PMMA. or we can just do a raster scan sort of blindly and just at each pixel stop and take the full spectrum. And so that's a sort of an overview of the technique. And the origin of the forces, so both the tip and the sample have a complex dielectric function. And when the tip is brought into close proximity of the sample, you can think of that as it has a net polarizability, that whole tip sample system. And if we could do a whole talk just on this concept, and so I put the reference up there. If you want to read more about the local force, basically is proportional to the fourth power of z. It falls off z to the fourth. But that's essentially what we're doing, is we're detecting local effective polarizability through the force exerted on the cantilever. And another way of thinking about it is that, so if the laser is focused onto the sample, it polarizes the sample. As the tip moves down into the focal spot, it too is polarized by the light, but it also becomes polarized by the sample polarization, which is, namely, that's the induced image dipole. And so that would be in phase with the sample polarization. So that D3 there is in phase with D1. And what we're reading out is with PIFM, the image force, is the D1 and the D3 interaction, which are in phase. And so just to sum up the simplicity of it, so with scattering SNOME, which is a complementary technique to PIFM, and in some cases yields similar results, you generally need an interferometer. You focus onto the tip. There is a PSD monitoring cantilever, there has to be, but then you have to recollect all the light, send it back through your optics, which are going to have some loss, send it into your photodetector, and then demodulate it according to the tip dither frequency, and also whether you did self-homodyne or pseudo-heterodyne, demodulated according to that. With PIFM, it's a lot simpler. Is you basically just focus onto the tip, and then the feedback electronics are what you use to demodulate and get your near-field signal. And so there's no light collection necessary, which makes it really nice. There's no need for an interferometer. You don't need a pricey detector that's only usable in some finite range. I sometimes say PIFM is sort of detector agnostic. There is no detector. So if we want to, if later the broadband laser gets expandable into even further wavelengths, we don't care, because we'll still detect it. We detect it through the cantilever. So it's only about illumination with PIFM. And so a terahertz source coupled with our instrument, we don't have to go find a terahertz detector. We have our detector is the cantilever, and we don't have to separate out this parasitic far field like with scattering SNOME. And so I'll just talk a slide or two on our instrument itself before turning it over to Tom to talk about the more fun stuff, which is the results. Our Vistascope platform was designed from the ground up to be a near-field microscope. You see a lot of stuff out there where it's an optical microscope retrofitted with an AFM, or vice versa, an AFM, and we're going to marry all these high NA optics, try to get it close. Since this was designed from day zero to actually do both, we have the most illumination pathways one can have. So we've got inverted side illumination, top illumination, and a rock stable AFM. Recently, we've added a vacuum enclosure to it. It comes in an acoustic enclosure, of course, and also we've in beta phase right now with one of our collaborators. We've added this reference arm for Michelson interferometer to do full scattering SNOME with the reference arm. So it's that modality is also available, and we're getting new results on that now. And then with the vacuum enclosure, that's kind of exciting to us, because our sensor is the cantilever, our near field sensor is the cantilever. As the Q factor increases, in theory, our near field sensitivity should increase. And this technique is the only one that can say that, right? So if I'm doing scattering SNOME and my AFM gets 10 times more sensitive, well, my near field signal may not have changed at all. But here, if the sensitivity of the cantilever gets 10 times more sensitive, in other words, the Q factor goes up, we should expect an increase in the signal to noise of our PIFM signal. And so, and it's because as the pressure of the vessel of the chamber goes down, the Q factor goes up. That's a known fact. And so we're just now running experiments on that. It's very exciting. And then we've added a lot of flexibility too. So if you want to add your own external laser source to be co-aligned with the IR laser, or directed to an inverted objective, parabolic mirror, there's an optical port for inverted detection where you could couple your own CCD, EMCCD, a PMT, whatever your favorite photodetector is. So even though PIFM is detector agnostic, but if you still want to do TERS, scattering SNOME, because we have this ample illumination and collection pathway, you can use that, and we accommodate that. So you won't find a more versatile platform to do any near field experiment that you have in mind. And so with that, I will turn it over to Tom.
Okay, well, thank you very much, Ryan, for giving us that nice introduction to the technique. And I will show you some of the results that we've been getting with this technique. Just a reminder that as we go through the presentation, you're welcome to type in questions, and we'll address those questions at the end of the presentation. And so you should be able to get some answers to those. Okay, so I will now show some of the results that we're getting with PIFM. And I'm going to start out with one which is really quite interesting. We did a live demo at the University of Minnesota a few months back. We packed up our instrument and took it there and had people bring in samples on the spot, and we were able to image them. And this was one of the more interesting samples we looked at, and it really highlights the kinds of things you can do with photo-induced force microscopy. This particular sample is a pharmaceutical composite comprised of three different elements. One is a PBMA, another is PLMA, and the other is dexamethasone. And we actually don't know much about these in terms of what they're used for from a pharmaceutical point of view, but we do know that we can image these things and chemically map them on the nanoscale. This slide I'm showing you right now is just some existing work that was done by the team that prepared these samples in the past. You see that it came from the University of Minnesota Characterization Facility, and then some sort of conventional AFM images that they had taken in the past on this material. And you can see it's got an interesting structure to it, and you can see the type of information you can get with conventional AFM using different modes like topographic height, adhesion, differential height, or loss angle stiffness. And already you can tell that there's differences among the different materials present here. But let's take a look at what PIFM can do here, because we can actually positively identify each of these materials chemically. Now, each of these materials has a distinct infrared absorption spectrum as measured conventionally by FTIR on macroscopic samples. And what we're showing in the center of the screen here is a conventional FTIR spectrum of dexamethasone. And as you can see, it has a number of absorption peaks. In this particular case, it's shown with a downward spike, meaning high absorption. So basically, there's sort of a transmission spectrum as it's shown. But those dips are the absorption peaks, and that's what PIFM will respond to. And so, for example, you can see how our images highlight one of the materials present in this composite. For example, upper left shows if we tune our laser to 1713 wave number, that corresponds to one of the FTIR absorption peaks that you see in that center image. And indeed, that lights up this particular material in the composite. And likewise, at several of the other peaks associated with this material dexamethasone, we can see the same kind of image. And that tells us that what we're seeing in these images definitely is the dexamethasone, because it correlates to the known FTIR spectrum. So the dexamethasone seems to be these small sort of spherical droplet-looking things that are in this background matrix, and it's not the larger round blobs that you see in there as well. Now, we can do this with all three materials present. And for example, as you look at this page, we've now plotted these in three different colors. First of all, in the lower left is our own topographic image, and you can see a lot of similarity to the AF images I showed in the previous work. Now, up in the top there in green, you see the dexamethasone, which is basically just the same image that I showed you on the previous slide. And then if we go to other wave numbers, for example, in the upper left, 1729 inverse centimeters, that's one of the absorption peaks associated with PLMA. And then on the right, PBMA at 1468. And then we can generate a sort of a false color image down below that shows how these materials are clearly identified with different elements in that composite. So the small round spheres are the dexamethasone, the large blue blobs are the PBMA, and sort of this matrix material in the background is the PLMA. Now, there's a little bit more to this one. If you look at the upper right image in blue, you see that the PBMA picture there at 1468 also includes a response to the small droplets. And we're able to differentiate those and know that only the large blue droplets are the PBMA because the dexamethasone picture in the center does not respond to those. So it turns out that dexamethasone and PBMA do share a peak at 1468, but we are still able to clearly assign what is what based on study of the three together. So this shows the power of what PIFM can do in terms of nanometer scale chemical mapping. Now, let's back up a bit and look a little bit more at the fundamentals of how this works and what some of the limitations are in terms of resolution and how sensitive it is. So here's an example of a black copolymer. This is a material which, when spin coated, it separates into alternating stripes of two different polymers. In red there you see PMMA, and in green you see polystyrene, and on the right you see the combined image. But let's take a look at the spectra on the bottom. If we were looking at a sample of PMMA homopolymer, which we actually did, then you can see that in red is shown the FTIR spectrum that's obtained on a macroscopic sample of this, and in black is the PIFM signal we get from this type of, say, uniform PMMA sample. And you see good correlation between the peaks that are seen in the PIFM versus the peaks seen in FTIR. You do see a little bit more structure actually on the PIFM peak in black there, and that's because there could be some water absorption present in that particular experiment that creates a notch in the peak there. Likewise, on the right lower picture, you see for polystyrene there, two different peaks that are highlighted in conventional FTIR also show up beautifully in the PIFM signal. So that allows us to know very clearly that which of these is which as we tune the different wavelengths. Now, in the upper left, you see the topography for this sample. And in fact, there's very little topography. There's only 2 nanometers of topography there. And from experience, we actually know that some black copolymer materials, when annealed and spin coated and so forth, actually have virtually no topography, but they still will have this alternating set of stripes. And the period of these stripes, the full pitch, is 40 nanometers. So each of those stripes is 20 nanometers wide. And as you can see, the signal-to-noise ratio is actually quite superb here. So this is really not at the limits of our resolution or sensitivity. This film is about 30 nanometers thick, so there's plenty of signal, and our resolution can easily handle features that are 20 nanometers wide. In fact, we generally put our resolution at about 10 nanometers, and you'll see more of that in the following slides. So on the next slide here is the same kind of material. This is another PMMA black copolymer, but one which is engineered to have a small full pitch. This is 24 nanometers, so each stripe is 12 nanometers wide, and yet you can still see very nicely, particularly the polystyrene shows up very strongly here. The PMMA though also has a usable signal. So here, as we approach 10 nanometer half pitch or 10 nanometer stripe width, we're still seeing nice images that can clearly differentiate the different chemical species via their IR absorption signature. So this supports the general notion that we have about 10 nanometers resolution laterally. Now, we believe actually it can probably extend further than this because analysis of the force shows a very strong Z dependence, which should indeed support even higher resolution than this. And that may be something we achieve in the coming year as we bring up our vacuum capability and so forth. So stay tuned. You may see in the future that we can do even smaller features than this. Now, what about vertical sensitivity? How deep into the sample are we sensitive, or what's the penetration depth of this PIFM technique? So here, we'll again use block copolymers. These are nice prototypical systems to help us understand how this technique works. Now, in this case, it's a different kind of block copolymer, which is actually forming what are called parallel lamellae, or basically layers laying horizontally on the surface. And they're alternating materials, in this case, PS and PTMSS. And it turns out these things can only form sort of integral pairs of layers here, as you see in the little diagram on the right. Each pair of material forms a structure that's 11 nanometers thick, and each of those is divided into two halves, 5.5 nanometers of PTMSS and 5.5 nanometers of polystyrene. And if you try to spin coat the amount of this so that it's not quite an integral layer, you'll end up with either sort of islands or holes on the top layer. And if you look at the topography on the left, you can see very nicely that we can see these islands and holes. And then if you look at how the PIFM signals correlate, the center column is PIFM images when we're tuned to 1493, which responds to polystyrene. So what you see in orange there is polystyrene, and what is blue or black is the absence of polystyrene in the center column. In the right column, we're tuned to 1599 wave numbers, and that's responding to PTMSS. So what's brighter there, or orange, is the presence of the PTMSS, and what's darker is the absence. And now if you look for correlations, you'll see that the rightmost column correlates to the topography shown in the leftmost column. So what that's telling us is whatever is sticking up, whatever is the highest level, is actually PTMSS. And we know, in fact, from work that's been done on this material in the past, that that's exactly what the situation is here. And the reason I'm showing this is that tells you that we can clearly see what's in the top layer, even when the top layer is only 5 nanometers thick. So the sensitivity responds much more in the first several nanometers than deeper than that. So that gives you an idea of the sort of depth penetration of this technique. And one more result here to sort of explore that particular topic of how deep do we see into the material, or conversely, how little material in a thin film can we respond to? Well, we looked at a sample of DNA origami. This is sort of a hot topic these days. You can form all kinds of engineered sizes and shapes of structures. These little triangles shown here are one of the classic formations that can be made by DNA origami. The structure is basically the thickness of a single double helix of DNA. So it's about 2 nanometers thick. And this is our own AFM topographic image of some of these little DNA origami triangles sitting on the background. And as you can see, we're seeing just slightly less than 2 nanometers thick in this particular measurement of the height of these structures. So what happens now if we try to sense these by PIFM? Well, in the bottom is just shown the topography there in black and white. And in the top row, we're looking at 2 different cases. The 3 images in the upper left are tuned to 1435 wave number, which is one of many appropriate peaks for sensing DNA. It corresponds to a bond that is known to exist within DNA. And the 2 images on the right at 1000 wave numbers, those are tuned for absorption by the mica. So on the left, you can see, although it's a bit noisy, the signal is there. We can pick up the presence of the DNA at 1435. And on the right, we can pick up the mica. And what's interesting there is you see sort of the dark triangle, which is the absence of the mica. In other words, a couple nanometers of this DNA sitting on mica is enough to pull the tip back a little bit in that area, and we don't see the mica signal as strongly. So this again points to the fact that this is very much a surface-sensitive technique, and you'll be able to see very fine layers of structures at the surface, which is great for looking like things like contaminants or process development issues and so forth. Okay, now naturally, since we get AFM topographic images for free while we're taking the PIFM images, you can superimpose the two and see the correlation of topography and chemical structure. This is a case where we're looking at a very thin film of PMMA, about 2 to 3 nanometers thick, that's continuous on the substrate. And then on top of that, there are some de-wetted droplets of polystyrene, which are a bit thicker. And you can can see very nicely here, we can see the PMMA background very strongly. And here again, it's only 2 to 3 nanometers thick. So that illustrates the sensitivity of this technique. And the droplets clearly correspond, the polystyrene PIFM signal clearly corresponds to the locations where we physically see the droplets in the topography. So topography and chemical information married together give very nice diagnostic technique to go after things here. Okay, now let's take a look at what we call the hyperspectrum. And basically, this is one of our favorite modes for operating the instrument because it provides a very rich and detailed data set. We can see, for example, a full spectrum, a full IR absorption spectrum associated with each pixel in the image. And it doesn't take long to get these images, maybe 1 hour, maybe 2 hours for an especially rich one with a very wide spectrum and lots of pixels, 256 by 256 and so forth. So compared to other near-field techniques, even our hyperspectral image is fairly quick. But in comparison, just so you know, when we want to take an image at a single wave number, it's basically less than a minute, or basically the same as a conventional AFM image. But when we take this hyperspectrum, we actually gather a full spectrum at each pixel, or conversely, you can think of it as a whole picture at each wave number. It's 2 ways of looking at the data. And this allows you to search through the data in very interesting ways after the hyperspectral image has been acquired. One way we can do it is simply at the top by looking at different wave numbers, which are captured within all that data. For example, we can choose wavelengths that highlight the polystyrene or the PMMA and combine those to form a chemical image. We can also do what we would call masking. If we look at the image in the lower left, we can choose certain regions to highlight and look at the average infrared spectrum that's occurring in those areas. So, for example, if we take the mask right here and make a little round region, which you can do yourself in the software, and then look at the spectrum that's associated with that, we see the polystyrene peaks as expected when we take the signal there, or the same for this blue region here. That's the blue line and the red line, which largely overlap here because it corresponds to polystyrene signal. Or if we take a mask that's in the background, we can see in the green line here something that corresponds to PMMA absorption. So that's one of the things you can do with that is to go in and highlight certain specific areas and look at the spectrum and use that to help understand what the chemical material is that's present in each area. Very nice diagnostic method. But what's really fun with these hyperspectral images is to look at a video where we actually sweep through a wide range of wave numbers and simply show the XY image. And what's going to happen here as I turn on this video is you'll see the image constantly changing, and that corresponds to the changing PIFM signal as we move from wave number to wave number. This particular sample is a 2D perovskite sort of organic solar cell type material. And it turns out to be a very rich composite structure that obviously ends up having many different phases of material present. The topographic image you see at the left gives some hints about that. You see sort of those 2 sort of cubic-looking crystallites poking out there. But also in the background, you see some sort of flaky structures, some particles, and so forth. But you're going to be very surprised at how much structure is revealed by the hyperspectral image. So let me go ahead and play this image now. And we're starting at around 1800 wave numbers. And we're going to sweep through here. You can follow the progress down here on this lower level. Not so much going on in this wave number range, but starting around here, now pay close attention to that image. You'll start to see different structures light up. There's one, there's another, these flakes. Very strong signal there. This is a very interesting one, something you would never suspect in the topography, and so on and so forth. You saw many changes occurring in that image as we sweep through the wave number range. This is just part of our range, 1800 to 1400. We can go farther than that, but this turned out to capture a lot of the interesting structure in this sample. Now, that's a bit fast to see it go by, so here's a sort of a freeze frame of what you see there. And by the way, you did see sort of some artifacts in that video, some snow and some vertical bars and so forth. That just had to do with the particular way we were displaying that video. The actual data is much cleaner looking. This is the real data taken from various wave numbers in that video I just showed you. And here again, this confirms that this is actually a very rich sample that contains a wide variety of different phases of material that have specific and different IR absorption spectra. One of my favorites is looking at this one in the center here, which shows sort of these needle-like or possibly edge-enhanced phases that the topography really gives no hint about, and you would not necessarily suspect is present. And yet it has a very clear and distinct PIFM signal that tells us that this is something unique and different about the material in these areas. Even things that look quite similar in the topography, for example, these two sort of cubic crystallites, at certain wave numbers, those have a different response. So it's possible that those two are materially different, or possibly that they have a different crystal orientation, which is interacting differently with the particular polarization of light that was used. So anyway, that just gives an idea of how you can use this in detective mode to see what all phases might be present. And if we had a lot more information about the specific chemical composition of this, we could probably learn to correlate these specific images with particular chemicals that are expected to be present in this material. All right, so here's another example. This is one that may appeal to the physicists out there. We're going to look at surface phonon polaritons in boron nitride nanotubes. Now, this slide isn't showing any PIFM. It's just a background slide to tell you a little bit about what this sample is. Now, first of all, what's a boron nitride nanotube? Well, you've probably heard of carbon nanotubes because that's been a very hot topic in the world of science for the last decade. Basically, you roll up graphite into a cylindrical form and you end up creating materials that have very special physical and chemical properties. Now, it turns out you can do the same thing with boron nitride. If you think about boron and nitrogen on the periodic table, they are the nearest neighbors of carbon. Boron to the left and nitrogen to the right. So if you substitute every other carbon with boron and likewise with nitrogen, you make another type of layered material, and this one also can form nanotubes. But this material has some very special structures called polaritons, which end up creating sort of interference patterns in terms of the IR absorption spatially. A very nice study was done by this group under Shaoji Xu, published a couple of years ago. They're looking at a couple of these boron nitride nanotubes on a substrate. This is the topography, and you can see that. And then this is known to have an IR absorption peak at around 1365. And then if you go up in frequency or wave number from there, you begin to see these wavelength-dependent interference patterns of bright and dark sort of fringes. And as we move farther and farther away from this absorption resonance at 1365 on the top side from a frequency point of view, these little interference patterns get more and more dense. And that was a very nice result done by scattering snow. And it turns out when we look at this with PIFM, we end up having a result that actually looks quite reminiscent of what is seen by scattering snow on this type of sample. So here we've taken some of these samples, also provided by Shaoji Xu at Lehigh in collaboration with Chunye Ji. And we're looking at this. So this is a topographic image of what we see of one of these boron nitride nanotubes. And some of the PIFM images, for example, if we image at 1746, the substrate shows up very nicely. At 1365, the carbon nanotube, or not carbon, boron nitride nanotube shows up because this is again the absorption peak. But what's interesting now, I'm going to show the variable wave number here as we cruise through a range of, actually this is our full tunable range. And in this image here, now you'll see the substrate light up at that particular wave number, as already mentioned. And then when we get into this region, this is where you'll start to see these polariton structures. And you'll see moving patterns here now as we change wavelength. They sort of smoothly vary as a function of the changing wave number. And that's characteristic of what's expected from these polaritons. And then they abruptly stop as soon as we get to the absorption peak, the 1365, then everything turns off after that. And At first, we thought those were the only polaritons we should be seeing on this sample, but we allowed our system to go ahead and take the PIFM images over our full tunable range from 1800 to 800, or 760 actually at the bottom end. And what you'll see here is there's another batch of polaritons that's available right out here. So watch closely now. Around 800, we also get these moving fringes. And we were not aware of this, but that actually is a known additional range of polaritons that was pointed out to us by attendees at a recent conference we went to. So in fact, we're seeing exactly what we should on this sample. So just to kind of zoom in on the first set of polaritons, we're going to just scan through this region around 1365 here. And if you look at the green image, now you can watch these patterns change a little more slowly as we particularly concentrate on that range of wave numbers where the polaritons are showing up. And likewise, we can do the same thing at the 800 range, and you'll see here again in the green image that last set of polaritons around 800 and the motion of the fringes. So this was exciting to us. It shows that, of course, we can use this for chemical mapping, which was our main objective with this, but we can also explore other interesting physical phenomena, such as the polaritons with PIFM. Okay, onward. Let's take a look at this business of the tuning range. You know, we've mentioned that we can tune from 800 to 1800 inverse centimeters, or wave numbers. And if you're a chemist and you've done lots of IR spectroscopy, you might be thinking that that's a bit of a small range. You know, there are a lot of chemical entities out there, for example, alkanes or carboxylic acid groups, for which you know, the primary peaks that people might first think about would be around 3,000 wave numbers. And that might be what you'd choose to look for in an FTIR spectrum to identify these materials. Now, of course, if we did have a tunable laser that could cover that whole range, we would use it and install it in our system and be happy with that. But tunable IR lasers are still an evolving technology, and that type of source is not easily available to us yet, whereas the quantum cascade laser that tunes from 800 to 1800 is working well for us. Now, you might think then with these peaks missing that we're losing a lot of our ability to identify certain chemical species. But it turns out that in most cases, the particular chemical materials that have these important peaks out in the 3000 range also have additional peaks that are within our tunable range. So if one is willing to look at alternative absorption peaks for these different entities, you can find them within our tunable range. I'm going to show you an example of that where we're going to use a peak here around 1470 to look at an alkane material. This is a CH scissoring mode rather than the usual CH stretch mode that people would use, but it's not inside our tuning range. And that is, we had a very interesting material brought to us. This is a vapor deposited acidic methyl ester that forms a very thin layer of about 5 nanometers thick on a silicon substrate deposited out of vapor. Topographically, it looks very nice. You see these little floweret patterns that form on an otherwise clean background. And then you could look at the PIFM images that were taken simultaneously. For example, if we choose a 1030 wave number, that again highlights the substrate, in this case, the silicon background. If we go to the 1463, that's the CH scissor mode. And indeed, we can see some signature of these droplets at that wave number. If we zoom in, we can make this a little bit more clear. Here in the lower right is a 1463 that resonates at that CH scissor mode and allows us to see that material. One other kind of interesting thing here is that I mentioned this was a vapor deposited material, so it obviously has a significant vapor pressure. When we hit the absorption peak, it does warm it up a little bit with this IR radiation hitting it. And as you can see here, the topographic image reveals that, in fact, some of the material has evaporated off the surface. We're left with sort of half a floweret at this point. Usually we're not heating things up very much, but for a very sensitive material like this one, which has a high vapor pressure, you can see a little bit of evidence that you can evaporate some of the material off due to the heating that occurs during the experiment. This is the spectrum that was taken and shows that we're able to see that 1464 CH scissoring peak, and that's how we identify that particular material. So bottom line is we can work with the range of tuning that we have to see many different chemical entities. And finally, I'll just throw in one last picture here showing a biological material, just to highlight that, we can look at biological materials. So if that's your main interest, this is a good technique for doing it. These are collagen fibrils, or single strands, actually, on a mica substrate. These are not the bundles. So the single strands being rather thin, just a few nanometers thick, we are able to see an amide 1 peak at 1666 wave numbers and correlate that to the topography that's associated with these individual strands. So biological materials are also a candidate. All right, so then just to kind of conclude here, we've got a number of different techniques out there. This is a chart from Evans Analytical Group that shows different types of techniques that are used for analyzing different materials as a function of analytical spot size on this axis, and also sort of a density in terms of how much material needs to be present. And for example, TOF-SIMS is one of the most sensitive and widely used techniques out there right now for chemical mapping at the very small scale. But as you can see, it kind of ends at around 100 nanometers spot size. So if you want to see smaller structures than that, there's really sort of an empty hole here. There's no technique that can address that area well. And that's exactly one of the things we think PIFM can serve as. It's an extension to these existing techniques that allows you to see smaller spot sizes and analyze smaller volumes of material. And we think this actually has a good chance to become one of the standard techniques out there that addresses this hole in the palette of different techniques that are available. All right, so then to conclude, PIFM generates IR spectra with nanometer scale spatial resolution, and this is ideal for chemical mapping of molecular materials at a scale much smaller than the conventional techniques offer today. The PIFM signal originates in dipole-dipole image force interactions between a metal tip and an illuminated sample. It's technically different than photothermal imaging, and it offers higher resolution. And the signet is qualitatively similar to what's seen in scattering SNOME, but it doesn't have the background scattering challenges of scattering SNOME, so we think it's an easier technique to realize. Very sensitive and high resolution. Hyperimaging, or hyperspectral, is a powerful technique that stores a full spectrum at each image pixel. And as you look through this data, you can see that individual chemical species light up at their specific IR absorption wavelengths. And we've shown a number of PFM images on various type of samples, polymeric, biological, inorganic, and also sort of the interesting phenomenon of the surface phonon polaritons. Okay, so with that, we're going to go ahead and stop. Thank you for your attention. And at this time, we'll be willing to take a look at questions that you may have sent in, and we can try to answer those for you.
Tom, we had one question asking if all these results were from the side illumination, and the answer is yes. That's the side path is where we illuminate with the off-axis parabolic mirror, and so anything that's in the IR basically, at least anything in this presentation, would have come from side illumination.
Yeah, and one thing I can add there, I think some of you would know why we use a parabolic mirror for this side illumination, but that makes a nice wavelength independent method to see a good focus that stays stable over our entire IR tuning range. So that's why we have that parabolic mirror for focusing the light from the side. And that's built right into the head with its own little 3D actuator system built right into the head so that we can align the focus spot of that parabolic mirror to where the tip is at.
Yep. We got another one, Tom. It says, what's the spectral resolution?
Yes. Okay. Yeah, I can address that one. I can see the questions now as well since I stopped sharing my screen. But so we got lots of questions here. But let's address that one of the spectral resolution first. Spectral resolution, we can take our spectra with a resolution of single wave number. And that's one of the reasons why our spectra often look quite detailed compared to what people are usually seeing by FTIR, which is often done at a lower resolution, like 4 or 8 or 16 wave numbers. So single wave number resolution. Let's take a look at some of the other questions here. The scanning size limitations. Our instrument right now can scan up to 30 by 30 microns, and we're working on some new scanner designs that may extend that to considerably larger scan sizes in the near future. But for now, the instrument off the shelf provides a 30 by 30 micron scanning range. Did we apply this technique to semiconductor devices? And the answer is yes, we have looked at various kinds of devices. I don't have anything to show you right now on semiconductor devices, but it is applicable. We've also done it with display type devices to organic materials in those. But basically, if you want to know whether the technique is going to be useful for a particular type of material or structure, the key thing is that it's that it be made up of different chemical species that have unique and differentiable IR absorption spectra. So, for example, if your semiconductor device contains a few different materials, whether organic or inorganic, as long as they have different IR spectrum absorption spectra within the tuning range that we have, PIFM will be able to highlight those materials individually. Now, not all inorganic materials have peaks within that range, so we don't want to suggest that every material will show up within our tuning range. But we also don't want to suggest that it's restricted to polymeric or organic materials. We often do see inorganic materials also showing different peaks in that range and being able to differentiate them. Okay. So let's see. Next question. In your example, how similar is the spectrum from PIFM comparing to regular FTIR in the 800 to 1800 centimeter range? So here, in general, we would say there is remarkably good correlation to the peaks obtained by FTIR, but it's not identical. We do see a little bit more structure. Not all peaks show up the same way. That's still an active area of study to fully understand it. Sometimes, especially our earlier data, it can be affected by water absorption in the air. And that's one of the reasons why our tool now, as you saw it, has a chamber cover that allows us to either evacuate or backfill with either dry air or nitrogen, because that prevents water in the air, which actually has quite a rich absorption spectrum and lots of sharp peaks, from sort of generating false structure on top of the peaks you're trying to look for from your sample. But bottom line is, we have very high resolution, so sometimes we're seeing detail that doesn't show up easily in FTIR. But overall, the correlation is quite good, and you can use FTIR absorption spectrum as a good guideline as what you should be seeing on these materials with PIFM.
Can I add to that, Tom?
Sure.
Yeah, to the gentleman who asked the question, actually, the splash screen right here, if you want more of a visual look at it, in the upper left there, the two bottom panels there, that's exactly what's shown there is a PIFM spectra and FTIR spectra for PMMA and polystyrene. It was also in the presentation, but if you want to just take a quick glance at that shows that the correlation in general is pretty good.
Okay, yeah, so next question is in a 10 to 50 nanometer organic film consisting of two-component blend where one component is present at a weight concentration of 0.1 to 1% by that weight in a thin film, can it be detected? Well, I would say the answer is probably yes, but it depends a little bit on how that small concentration component is segregated. If that were segregated into extremely tiny things, say, for example, little spheres that are, say, less than 1 nanometer, those would be challenging to see. But, for example, if they're segregated into relatively sparse droplets that are a little bit larger than that say are a good 10 nanometers wide and at least a couple nanometers thick, then we'd have a better chance to see it. And if the size were larger than that, we would certainly be able to see it, as long as it had a distinct IR absorption spectrum from the background or matrix material. Another question here says, would you be able to identify boron or arsenic in a PN junction? And that one I'm not going to venture to answer off the cuff, because here again, we'd want to know what the macroscopic sample would show in terms of FTIR spectrum. Do we know that those materials should have unique and different IR absorption spectrum within our tuning range? Ryan, anything you want to add to that one? Do you know anything more specifically about that question?
I don't know specifically about it, but a lot of times when it's like that, where I don't know, it's a lot of. Please talk to us afterwards. We do have image samples very routinely with our in-house system. A lot of times, the best way to answer it is to try it. And so, feel free to get in contact with us afterwards to discuss if you want to arrange to have a sample sent out.
And I think one thing we can add here is sometimes you see good contrast, even though you're not at a known IR absorption peak. All we really require is that the absorption be distinctly different between the two materials. And quite surprisingly, sometimes far from the main peaks, you can still see very strong contrast between the two different materials. So we certainly would not rule that out. And it may be worth a shot. But as Ryan says, we'd be happy to talk more about that afterwards. Okay, Z piezo range is about, we have a dual Z, a fast Z in the AFM head and a slow Z in the sample holder. The fast Z is about 1 or 2 microns, depending on how we have it configured. And the slow Z is, I think it's around 7 or 8 microns. I forget the exact number there. But so we're on the order of 10-ish in terms of the total Z piezo range, maybe a little bit less. Okay, I use phase imaging a lot in polymer study. I will probably use phase image to locate the domain interested and then do PIFM on it. Do you have a phase imaging mode? And the answer is yes, we do. We didn't happen to show any of that data today, but we have done that on various samples, and you often get a very nice correlation of what's being seen in an AFM phase image to what's being seen in PIFM sample. Okay, and last question, do we want to answer that here on the air or save that for individual discussions?
Let's have a private discussion on that one, I think.
Yeah, exactly. So we're going to leave that one up. Contact us in private for more discussions about the price of the instrument. There are many different things that apply there in terms of configurations and so forth. So we don't want to just toss out a single number here that tries to represent that. Okay. Let's see. One more question here. I think I've seen images on graphene, not sure, in the introduction slide. Am I correct? And the answer is yes. With some confocal Raman that was shown there, and also some PIFM. Can you describe the result you get, and what was the sample exactly, and so on and so forth? Sung, you might be in a better position to answer this one.
Is a single layer.
Go right ahead and answer this one. Sung's here and he'll answer it.
Yes, that sample was flakes that was transferred onto a sapphire substrate. I'm sorry, quartz substrate, and had well-defined single and double and multiple layers. And we were able to see a clear signature based on, I believe, optical conductivity, basically. But basically, what we find is that since we are measuring the polarizability, each layer adds kind of a quantum level of signal. So we can actually detect different layer thickness just by looking at the PIFM signal. But again, we can talk further after the meeting if there is more information needed.
We got another question asking, do we provide analysis services or do we need to buy the equipment? Actually, we do work on contracts on occasion. We can provide our services and work out a contract for that. So feel free to get in touch with us about that.
Okay, it looks like that has covered all the questions that came in. So we thank everyone for attending the webinar this morning. Lots of good and interesting questions. Proves you're paying attention and interested in the material here. And feel free to contact us further with any follow-up questions you may have, or if you've got any interest in purchasing the equipment or having some samples analyzed. We will also post the webinar, so that will be available to people to look at further afterwards. We do have another webinar coming up later today at 6 p.m. Pacific time, in case anybody else is interested in seeing that and wasn't able to join at this time. All right, with that, we will conclude the webinar. Thank you for your attendance.